Welcome to the webinar, Hard Real-Time Data Management over Persistent Storage Media. Devices in embedded systems, real-time systems, and the Internet of Things are data-driven. Let's face it, it's all about the data. The whole purpose of these systems is to acquire data, act on that data, and especially for the Internet of Things, share that data. Until now, flash memory technology stacks presented significant challenges for real-time data management due to the presence of background tasks for garbage collection, wear leveling, and error correction. Hard real-time data management, the only kind we will be discussing in this webinar, is all about guaranteeing transaction deadlines. The normal workflow is to start a transaction, perform some CRUD operations, and commit the transaction. But typically, there's no deadline for that begin work commit sequence. A real-time database system changes that by adding a deadline as a parameter to the transaction start function. The usual tech stack for NAND flash presents unique challenges for guaranteeing transaction deadlines. That stack consists of a low-level driver, a flash translation layer, a file system, and a database system. File systems know nothing about database deadlines, and they introduce unnecessary overhead for metadata. So we can get rid of the file system and use flash as a raw block device, which is the interface that the flash translation layer exposes. But FTLs also don't know anything about database transaction deadlines, and they implement background tasks for wear leveling, bad block management, and so on that introduce unpredictability. This presentation explores how we can address these issues using a transactional flash translation layer, or TFTL. Traditional real-time scheduling algorithms, such as EDF and RMS, help prioritize transactions based on urgency. Very briefly, if a system has multiple tasks or threads that need concurrent access to the database, then a queue of transaction requests needs to be maintained and scheduled according to tasks' priorities and deadlines. Copy-on-write, or COW, is a preferred mechanism for flash-based storage as it avoids in-place modifications, maintaining real-time constraints while simplifying recovery. Copy-on-write also harmonizes with wear leveling, meaning that with flash, you can't modify data in place anyway. To perform an update, you have to read the block, update the contents, and write the block to a new location. This spreads out the writes over the flash memory blocks. Database systems more typically implement a write-ahead logging, or WAL, implementation. WAL is more performant, but in real-time systems, predictability trumps performance. With copy-on-write, we maintain a list of committed pages and a list of current pages. When a transaction commits, all we have to do is switch the current list to the committed list. If a transaction aborts, we just throw away the current list, and the committed list that existed before the transaction started remains the committed list. Write-ahead logging is more complicated and inherently unpredictable because we can't know in advance how long a transaction is, and thus how many pages have to be transferred from the log to the database. All database systems must guarantee the internal consistency of the database. Real-time database systems also need to guarantee the external consistency of the database, or to put it another way, the temporal consistency of the database. That means that the content of the database should reflect the real world within a specified timing constraint. In other words, within the transaction deadline. For example, if the deadline is 100 milliseconds, the database reflects the real world within the last 100 milliseconds. When a real-time database is maintained in flash memory, wear leveling, garbage collection, and bad block management have the potential to introduce delays if they're not made transaction aware. In other words, aware of deadlines. All persistent storage mediums have read-write asymmetry, but it's more pronounced in flash memory. Again, flash memory doesn't allow you to write over an existing page. In practice, if you need to write bytes 100 to 150 within a 512-byte page, you have to erase a new page, copy bytes 0 to 99 from the original page, write the new 100 to 150 bytes, then copy bytes 151 to 511 from the original page. This is done in a buffer, which is then written as a whole to the new flash page. In fact, it's worse than that. An erase block is the smallest chunk of memory that can be erased at once, usually 256 kilobytes, and is thus made up of multiple pages. A flash translation layer typically exists between a file system and the flash hardware. It abstracts the complexities of wear leveling, etc., and presents the flash memory as a simple block device to the file system. That means there are background activities taking place within the FTL to implement wear leveling, etc., and we have no control over it. File systems introduce another layer of overhead and unpredictability. File systems and FTL represent black boxes to database systems in that we can't know and can't control what is going on within them. And for deterministic performance, a requirement of real-time systems, that is, a bad thing. NAND flash is optimized for high storage density and sequential write performance, making it the preferred choice for database storage and real-time systems. Despite its advantages, NAND flash requires aggressive wear level handling, bad block handling, and error correction. NAND flash memory is further categorized into two types: managed NAND and unmanaged, or raw NAND. Unmanaged NAND requires the host system to handle critical management tasks, including wear leveling, distributing write operations evenly to prevent premature degradation, bad block management, detecting and remapping faulty blocks, error correction codes, or ECC, as a part of the host driver, ensuring data reliability. Managed NAND provides a convenient solution for general-purpose storage, but hides critical flash operations inside an internal controller, making real-time transactions all but impossible to guarantee. This abstraction can introduce delays when the controller performs background tasks like garbage collection. Unmanaged NAND, on the other hand, allows direct control over memory management, making it preferable for real-time applications where precise timing is required. However, using raw NAND requires robust software to handle wear leveling, bad block mapping, and error correction efficiently while maintaining predictable response times. For these reasons, a real-time database requires unmanaged NAND. The way NAND flash is connected to the system also affects performance. Parallel NAND interfaces transfer multiple bits per clock cycle, enabling high-speed data access, making them well-suited for database storage applications. Serial NAND interfaces transfer data 1 bit at a time per clock cycle, though some support 2 or 4-bit transfers, simplifying hardware design at the cost of reduced bandwidth. The ONFI standard helps standardize these interfaces, which simplifies hardware and software development through standardized chip identification and data exchange protocols, providing additional services such as internal data copying without CPU intervention, and even physical specifications, including package dimensions and pin layouts. Regardless of the connection method, flash memory access times remain predictable. Flash hardware is eminently suitable for real-time systems. Manufacturers specify precise time parameters for each operation. For example, chip select, serial clock, serial input, and serial output. It's the software stack on top of the hardware that needs to be made aware of real-time constraints. The FTL allows databases to use NAND storage without handling raw flash complexities. It maps logical blocks to physical blocks, implements wear leveling to maximize the useful life of flash memory, and when blocks do degrade, handles bad block management. However, standard FTLs have no concept of deadlines. The transactional FTL that we are presenting combines the best of both worlds. Flash memory management and transaction deadline guarantees. It directly integrates database logic with NAND storage handling, reducing unpredictability. Very briefly, the database runtime has a transaction scheduler that queues transactions according to policies, priorities, and deadlines assigned by the application. When a transaction is scheduled to run, it is dispatched to the TFTL. Data writes must be performed in whole pages. It is not possible to write part of a page and append additional data later. Reads can be partial. A portion of a page can be read without requiring the entire page. If partial reads are not supported, the entire page is read, and only the required portion is copied. Error correction codes, or ECC, are computed and stored automatically. During a write operation, the driver or hardware calculates an ECC and saves it in the spare area. ECC is verified during reads. The ECC is recalculated and compared with the stored value. If a mismatch occurs, an error correction mechanism attempts to fix the corrupted bits. If correction is not possible, an error is returned. This error gets percolated through the stack, ultimately returned to the application as a fatal error code. Fatal, meaning unrecoverable. Database operations cannot continue. Pages must be erased before writing. Typically, an erase operation is performed at the block level, where a block consists of multiple pages, typically a power of 2. We will examine 3 fundamental concepts of the TFTL: mapping, garbage collection, and transactions support. Due to the flash requirement erase before write and the copy on write algorithm, physical database pages move around. To simplify, a logical page pool is mapped to a physical page pool. During a transaction, every update operation triggers the copy on write policy, which we see in the diagram here. Logical page 9 was originally mapped to physical page hex 23, but remapped to physical page hex 226 due to the update. Hex 23 remains linked to logical page 9 as a stale page that will be garbage collected later. The head is the position where the next page will be written, whether it's a new page or an updated version of an existing one. Pages are always written sequentially, one after another. When the last page on the flash is reached, a wraparound occurs and head is reset to the first page, position 0. In this context, a reachable page is one that can be accessed by traversing from the head. For simplicity, if we disregard the tree structure over the logical page pool, TFTL searches backward from head, moving left, while looking for a page with the required logical address. The first match found represents the most recent, current version of the page. Any older versions of that page, located further to the left, are considered unreachable. As I mentioned earlier, TFTL actually maintains 2 page maps. The committed map, representing the last stable, consistent state, and the current map, a temporary map created during a read-write transaction. This diagram illustrates what happens when 2 logical pages, 28 and 56, in light red at the top of the diagram, are modified. In the committed map, these pages are mapped to hex 225 and hex 976. The green physical pages representing valid committed data. The transaction does not modify this map. Instead, it operates on the current map, which initially starts as an exact copy of the committed map. During an update, TFTL allocates new physical pages for the modified logical pages. As we said before, pages are never updated in place. In this example, 2 pages are updated, so 2 new pages are allocated, and the head pointer advances 2 pages from hex 977 to hex 979. The previous versions of the updated pages become stale, making them candidates for garbage collection when the transaction commits. To assess the effectiveness of TFTL, performance benchmarks were conducted to execute typical database insert, update, delete, and search operations. The benchmarks were configured to use either X-File or X-Flash database kernel modules. The X-File is a standard copy on write-based transaction manager running over a conventional FTL module. The X-Flash is a transactional FTL, integrating database transactions directly into the flash translation layer, replacing the intermediate block device layer. As you can see, X-Flash reduced I/O overhead significantly. The diagram shows the I/O volume for read, program, erase, and copy operations was up to 4 times lower in X-Flash. They're red bars compared to X-File, the blue bars. Additionally, total I/O time was reduced by 2 to 3 times, demonstrating the benefits of a tightly integrated transactional FTL. Integrating database transactions with flash memory management is key to keeping storage performance both predictable and efficient. The approach we have discussed provides a scalable and practical solution for embedded systems that rely on NAND flash as their primary storage medium. With a transactional flash translation layer, or TFTL, databases can run more efficiently, reduce I/O overhead, and, when needed, meet strict real-time constraints versus a database running on top of a flash file system or even the block device interface exposed by non-transactional FTLs, making it a solid choice for both real-time and general-purpose database applications. TFTL and other topics discussed here are explained in greater detail in the white paper Real-Time Data Management on NAND Flash Storage, available at www.macobject.com. Looking ahead, there's still room for improvement. Fine-tuning transaction scheduling, refining flash media management, and making TFTL's deadline management even more precise are all areas worth exploring. Another practical step forward is expanding low-level flash management libraries to better support both serial and parallel NAND flash across different manufacturers, making it easier to integrate with a wider range of embedded systems. This concludes our webinar. Please don't hesitate to reach out to us if you have any questions about this presentation or hard real-time database management, or if you would like evaluation software for your target system. Thank you for your time.